This is a continuation of a previous video, the subject of which is getting the most out of PEST. Now let's turn our attention to the calculation of finite difference derivatives. As we've discussed, PEST relies on the integrity of a Jacobian matrix to calculate good parameter upgrades. The Jacobian matrix is a sensitivity matrix. Each column of the Jacobian matrix ideally should contain the partial derivative of all model outputs used in the inversion process with respect to one parameter. The first column contains the derivatives with respect to the first parameter. The second column contains derivatives with respect to the second parameter, etc. If PEST is using finite differences to calculate these derivatives, as it normally does, the filling of each column of the Jacobian matrix therefore requires at least one model run. So the Jacobian matrix can be an expensive matrix to fill, especially where we're working with large numbers of parameters. Now, the variables which govern how finite difference derivatives calculation is undertaken reside in the parameter group section of the PEST control file. That's these variables here. They control the way finite difference derivatives a calculation is undertaken. The parameter group section of the PEST control file is also instrumental in setting up preferred value regularization in ways that we have just discussed. But for the moment, I point out that the variables which govern finite difference derivatives calculation are assigned to parameter groups rather than to individual parameters. So suppose we plot the value of a model output against the value of a parameter. The easiest way to calculate a finite difference derivatives is just by incrementing the value of a parameter, running the model with the incremented value of the parameter, subtract the difference of model outputs, divide by the differences of parameters, and then use the slope of this line as an approximation to the derivative at this point. The derivative, of course, is the tangent at that point. Obviously, the larger the increment, the less good is the slope in approximation to the tangent. However, if we make the increment too small, then we take numbers from each other, model outputs, parameter values, that are very close together, and by subtracting numbers that are very close together, we lose significant figures at the front of those numbers, and that can degrade the accuracy of derivatives calculation considerably. So the increment to use in finite difference derivatives calculation is a compromise. Optionally, we can use 3 points to calculate derivatives. This requires 2 model runs per parameter per iteration. The value of the parameter is incremented and then decremented. When this is done, PEST gives us 3 options for how to actually calculate an approximation to the derivative at the central point on the basis of model outputs and parameter values here, here, and here. Option 1 is to join those 3 points with a quadratic function, then differentiate that quadratic function to get the derivative at the central point. That's the most accurate, but only if model outputs are well behaved with respect to changes in parameter values. Another option is just to use the outside points. That may work if model outputs show granularity, something we'll talk about shortly. A further option is to do a least squares fit between those 3 points. This is a method of last resort if model outputs show significant granularity. If we do have a situation where model outputs looked at under the microscope look something like this, then we do have a problem, and perhaps we need to resort to 5-point derivative calculation. PEST provides that option, and if we have a 5-point derivative stencil, we can use those 5 points in two different ways. We can either obtain a minimum variance solution to this interpolation problem to give us an approximation to the derivative at the central point, or we can do a maximum precision option. Minimum variance is normally the best. This, of course, requires 4 model runs per parameter per iteration. The fifth is left over from the previous iteration. It's the current model output pertaining to the current value of the parameter, so we don't have to do that model run. So what are the best settings then to use for finite difference derivatives calculation? Generally, I set the inc type variable to relative. That is, I say I just want to vary each parameter by 1 or 2% of its current value as the increment for that parameter. However, if a parameter becomes very small in value, 2% of a very small value is a very, very small value, so sometimes it may be worthwhile telling PEST that there is a lower bound on the increment that it would use for any parameters in that group. That is supplied through the Derink LB control variable. I normally start off the inversion process using 2-point derivatives. That's 1 run per column of the Jacobian per iteration, 1 run per parameter per iteration. However, when the objective function doesn't fall very far, I would then like PEST to start using 3-point derivatives. That's 2 runs per parameter per iteration. This is achieved by setting this forCen variable to switch. When I do, I double the increment. That means I have a little bit more defense against model output granularity, but the loss of precision that's incurred through that is not enough to offset the significant gains accrued through using a 3-point stencil for finite difference derivatives. And then I choose parabolic as the method through which model outputs and parameter values at those 3 points are used to calculate a finite difference derivative. If we do switch to 3-point derivatives, the next question is, when do we make that switch? This is the variable in the control data section of the PEST control file which tells us when to make that switch. By setting it to 0.1, which I normally do, that informs PEST that it must make the switch from 2 to 3-point derivatives calculation if the objective function has not fallen by more than 10% during any iteration of the inversion process. Sometimes, however, we may run into trouble through following that protocol. If parameters have to change a lot in order to minimize an objective function, in order to get a good fit with a calibration dataset, then perhaps the changes that they undergo in the early iterations are not enough to lower the objective function by much. These variables here, rel parmax and fact parmax, limit how much any parameter is allowed to change during any iteration of the inversion process. Normally I set those to 10. This protects us against numerical instability, which can happen if parameters change too much. They can overshoot and we don't find the minimum of the objective function at all. So it is possible then for the inversion process to switch prematurely into the use of 3-point derivatives just because parameters aren't able to change as much as they'd like to lower the objective function in early iterations of the inversion process. That premature switching to 3-point derivatives calculation can be prevented using this NOPT switch control variable, which is situated in the control data section of the PEST control file. This is optional. I often use it and set it to 3 or 4, in which case I'm telling PEST don't switch to 3-point derivatives until iteration 3 or 4, even if the objective function does not fall by more than 10% during any of the preceding iterations. However, if the objective function rises instead of falls, then switch to 3-point derivatives calculation. In the previous section, I mentioned model output granularity. Let's look a little more at this issue. Ideally, if I were to plot any output from the model that I'm using in the inversion process against the value of the parameter, I'd like a curve like this, smooth and differentiable. Often, however, the curve is more like this. And this then creates problems for PEST because obviously differentiability is lost. Not completely lost, but it's certainly not as good as it should be. So if I can do anything to mitigate this problem, I should. If I can make outputs more continuous by doing something to the model, that's my first option. If I can't, there is a plan B, which we'll talk about later. There are things we can do with PEST that will give it some tolerance for this situation. But firstly, what are some of the things that I should look at with the model that I'm trying to calibrate? Well, a fundamental thing is this first point here. We should always ask a model to write numbers to its output files, if we have any control over this matter, to write numbers to its output files using as many significant figures as it can. Say, for example, a model only writes to its output files with 3 significant figures. When we vary a parameter incrementally, take one number from another, then if those numbers are very close together, perhaps we've lost all those significant figures in the differencing. That causes model output granularity. If we can adjust the model output protocol in any way, because the model gives us some control over this, we should ask that model outputs be written to the model output file with maximum precision. If our model is comprised of a batch or script file, with multiple executables running in succession, perhaps a preprocessor, the model itself, and then a post-processor, we should ensure that numbers are passed between those executables, once again, with maximum number of significant figures that we can, or even through binary files where all significant figures are automatically retained. If our model is a complicated numerical model such as a groundwater model, which has an iterative solver, we should set the convergence criteria for that solver quite tightly. In ModFlow, the variable which allows us to do that is called hclose. We should set that to 10 to the minus 5 or 10 to the minus 4 rather than 10 to the minus 3, which would be okay if we weren't calculating finite difference derivatives. Sometimes, if a model uses adaptive time stepping, that can cause problems. Ask yourself whether the model really needs to use adaptive time stepping when being used with PEST. Sometimes, however, the problem can lie in the actual design of the model, and this can be subtle, and I'll show you an example of this. This is a model that I built many years ago to look at the issue of irrigation demand. It's a simple model built around a soil moisture store. And this soil moisture store is present in many models, rainfall runoff models, land use models, so it's not an uncommon modelling device. The soil moisture store is filled with soil, a porous medium. The more water that's in the store, the more rapidly can water drain from the store. So there's a nonlinear function which relates rate of drainage to soil moisture content. The more water is in the store, the more easily can water evapotranspire from the store. And another nonlinear function relates evapotranspiration rate to water content in the soil and, of course, evaporation demand. And then there are two thresholds built into this model. If the water level drops to this lower threshold, the model demands irrigation. It is then filled to the upper threshold, this simulating roughly what happens at a farm scale. However, if it rains, the soil moisture store can fill beyond that threshold up to the top and runoff can occur. So let's look at the operation of this model conceptually. This top plot shows rainfall as a function of time. This purple plot shows the water level in the store. It falls, then it rains. The soil moisture store fills up, overflows, runoff takes place. Slowly it empties. At this point we reach the lower threshold. Irrigation is demanded, and so irrigation is supplied. The soil moisture store is filled to the upper threshold. Then evapotranspiration takes place as crops are grown. Just here it rains, so we don't need irrigation. Rainfall has supplied the water instead. But suppose that the soil moisture store had just a little bit less volume, soil moisture storage volume available to water. Then here we are on this part of the curve where evapotranspiration is taking place, and because the amount of water that can be stored in the soil water container is less, in this case we reach this lower threshold before the rain rather than after the rain. Irrigation is demanded and supplied. Hence, the outcome of this process is a discontinuous relationship between demand for irrigation and the volume of the soil moisture store, which may be a legitimate adjustable parameter. So there's a fundamental flaw in the design of this model if this model is going to be used for data assimilation processes, which is often the case for the decision support modeling for reasons discussed in another video. I can easily fix this just by modifying the design of this model. Instead of trying to simulate what happens on a farm and try to make the model too physically based, I should try to simulate what happens over an average of many farms, because my records of irrigation demand at pumping stations pertain to many farms rather than just an individual farm. On average, the water level in a farm will be the water level averaged over soils in all farms will be half full. These containers, as they pertain to soil moisture stores over many farms, on average the water level will be half. And this is what I need to simulate in my irrigation demand model. So I changed the design somewhat. If it rains, the water level, the average moisture store, fills up and possibly overflows. Then if it doesn't rain, evapotranspiration takes place till we get to half full, this representing the average situation over many farms. And then I demand irrigation on a day-by-day basis. Irrigation demand is satisfied in accordance with the demands for irrigation on that day. Then my relationship between irrigation demand and soil moisture store size and any other parameter is continuous. In changing the design of the model, I've lost something. It's not quite as physically based, it's not quite as representative as what happens on any one farm. However, I have made the outputs of the model continuous with respect to all parameters. This model is now capable of assimilating information pertaining to historical regional demand for water. The model's a little abstract now. Perhaps the properties that I ascribe to the soil moisture store are not something that I could as readily measure in the field on any one farm. Nevertheless, the model is suitable for data assimilation. Now, this matter is discussed a little in the literature, in my opinion, not enough. This paper by Kvetsky et al. I think is a very important paper. It points out that unless we design a model properly, we may end up with discontinuous relationships between model outputs and parameters. These will give rise to local optima, and these local optima are simply an artifact of poor model design, given that the role of the model is data assimilation. So, if we do have discontinuous relationship between model outputs and parameters, and if the discontinuities are too bad, either because of poor model design or because of other aspects of the model which we've already discussed, then PEST will not perform as well as it should. And when I say it won't perform as well as it should, I mean that the objective function won't fall as much as we think it should. We won't get as good a fit between model outputs and field data. Or the objective function will fall rapidly at first and then stop falling like it's hit a hard bottom. Or it'll fall and then rise, and then fall and then rise. All these are indications that something seems to be wrong with respect to differentiability of model outputs with respect to parameters, and PEST performance is suffering as a result. If we are seeing this kind of behavior when we're using PEST, we can test whether the cause of PEST's malperformance is in fact granularity, numerical granularity of model outputs as parameters are varied. A utility, one of the utilities supplied with the PEST suite is named JACTest for Jacobian testing. This shows you how it can be run from the command line. So JACTest reads a PEST control file. It reads in particular the parameter group section of the PEST control file, where the way in which finite difference derivatives calculation is specified. The user asks JACTest to vary one parameter. You select that parameter. And then JACTest varies that parameter incrementally a number of times. I normally say 10 times, by the same increments that are used for derivatives calculation. Then it records an output file that you can easily import into a spreadsheet such as Excel, and you can look at how all or any and all outputs of the model that are used in the calibration process vary as a function of incremental changes of that parameter. Here are some graphs from a recent use of JACTest, when I recently used JACTest. And as you can see, the relationship between some model outputs and the particular parameter that I chose to vary is pretty miserable. PEST's performance is severely challenged under these conditions. So JACTest gives you the ability to see the numerical situation that you're working with. Another utility named PostJACTests will post-process a JACTest output file, so the worst offending model outputs are placed at the top of the file, so you can see at a glance the how bad your situation is. So if that is the situation and you can't do much about it, either through changing the model design or changing the properties, the way that the model outputs are calculated through its iterative solver, if there's nothing much you can do, you just have to live with it. If numerical granularity is too bad, PEST won't work. But if it's not too bad, there are some defenses that you can take against this to mitigate the effect of this phenomenon on PEST performance. These include using a larger parameter increment, maybe employing a 5-point finite difference stencil. That's expensive. You can use PEST HP with, and it undertakes a line search along lambda upgrade directions, or we can undertake split slope analysis. I'll explain the last two of these now. Suppose we just have two parameters, and suppose that these are contours of the objective function in two-parameter space. If I have numerical granularity of model outputs, these objective function contours will not be as smooth as I like. Yes, there may be a minimum down here, but there may be ridges and valleys superimposed on these contours as a numerical artifact of unclean model outputs. Now, as we talk about in another video, every iteration of the PEST inversion process is divided into two parts. In the first part of every iteration, we calculate the Jacobian matrix. That's where we do finite difference derivatives. In the second part of every iteration, we then try different Marquardt lambdas and see how well they can allow us to upgrade the parameters. If we're using PEST or PEST, we do one model run for each lambda that we want to test. So we've got a situation like this. Here's our current best parameters. Here's different directions in parameter space, born of the use of different Marquardt lambdas. We do one run in each of those directions, choose the one that's lowered the objective function the most, and accept that as our upgraded parameters. However, if we've got ridges and valleys, this can interfere with this process. Maybe this single model run will take us to a ridge or a valley. It would be much better not to undertake one single model run in each of these lambda-defined directions, but do a line search along each of these directions. And that is what PEST HP does. HP stands for highly parallelized or high performance. It's built to work in an environment where we have many computer cores at our disposal and where we then have the ability to do multiple model runs in each of these directions. By doing that, we're most unlikely to find ourselves on top of a ridge or in a valley. We've got a much greater chance of finding our way towards the actual minimum of the objective function than if we just do one model run in each of these directions. So using PEST HP can give us some defense against problems incurred by model output granularity. And or we can use split slope analysis. There's three optional variables which can be placed at the end of this line in the parameter group section of the PEST control file, which tell PEST how to do, or PEST HP, how to do split slope analysis. And the idea is this. Suppose this is the value of a parameter along the x-axis, and this is the value of a model output along the y-axis. This is the output corresponding to our current best parameter value. So we increment the parameter when we're doing finite difference derivatives, and we're assuming that we've got a three-point finite difference stencil. We increment the parameter, and perhaps this is the model output. Then we decrement the parameter, and perhaps this is the model output. Now this situation looks highly suspect. These lines slope in the opposite direction. Perhaps this indicates that there's some ill behavior of the model that is contributing to one or both of these outputs that have caused these outputs to be so different between the increment and the decrement of the parameter. Under these circumstances, I can tell PEST to do one of three things. Take the lower slope, because on the basis that it's likely to be better number, and the higher slope is an outcome of model numerical malperformance. Or I can say set the derivative to 0. Let's assume as a safety measure that the parameter is just insensitive, because either of these, that's assuming a derivative of 0 is better than assuming that or that. or I could use the derivative from the previous iteration. That's my choice. I select that through these variables. Of course, we have to be using 3-point derivatives to use split slope analysis. That can happen if we use 3-point derivatives from the beginning of the PEST inversion process, or it may happen after we switch from 2-point to 3-point derivatives calculation. Now let's turn our attention to something completely different. I want to say a few words about observation groups. The observation groups that PEST uses are listed in the observation group section of the PEST control file. Normally, and every observation and every article of prior information has to be assigned to an observation group. And what I'll normally do is put observations of different types into different observation groups, or observations that I think inform different parameters into different observation groups on the basis of the fact that their information content is somewhat different from that of other observation groups. During each iteration of the inversion process undertaken by PEST, PEST lists the contribution to the total objective function made by each observation group. In this example, this is the total objective function. Here are objective functions calculated for each observation group. These are measurement observation groups. These comprise the measurement objective function, because this is an example of where we're running PEST in regularization mode. Here are the contributions made to the total objective function by regularization observation and prior information groups. Now, these are handled in a special way because of the way PEST handles Tikhonov regularization. As we've discussed, it applies a weight factor to these groups. Normally, the focus of my attention will be these: the contributions made to the objective function by observation groups pertaining to measurements. The objective function, the measurement objective function that I'm trying to lower through history matching. Now, at the start of the inversion process, perhaps I've got a situation like this. I've put my initial parameter values into a PEST control file. I've set the NOPT max variable, the number of iterations, in the control data section of the PEST control file. I've set NOPT max to 0. I run the model just once, just to make sure that everything's okay and that PEST can run the model and read its output files. And then PEST will write a short run record file in which it records the contribution to the total objective function made by each observation group. Perhaps it's something like this. First, let's look at the regularization groups. Well, if I'm using preferred value regularization, and if the preferred value for every parameter is its initial value, then at the commencement of the regularized inversion process, these contributions will be 0 because parameters are at their initial values. However, I may have a situation like this, where the contribution to the total objective function from each observation group comprising the measurements is very different. Now, this may not be a good thing, because if, as I just said, I divide observations into different observation groups on the basis that they inform different parameters, different aspects of the system, then I want the information which is contained in those different groups to be heard by PEST so that it can adjust parameters accordingly. And if one group is very small, its contribution to the objective function is very small compared with others, or if one group dominates, then perhaps PEST won't see the information that is resident in some observation groups. This is easily rectified by adjusting weights in the PEST control file such that the contribution made to the total objective function by each measurement observation group is roughly equal at the commencement of the inversion process. That can be done manually, or it can be done with the help of a utility named PWT-ADJ1, which was built for this purpose. PWT-ADJ1 stands for PEST Weight Adjustment 1. So my workflow may go something like this. I set up my PEST input data set. I divide my observations into groups on the basis of different observation types or on the basis that they're informing different aspects of the system. Within each group, I certainly give more credible observations a higher weight. If some observations are noisy, they'll get a lower weight. So the weighting reflects observation credibility within each group. I set NOPMAX to 0, that control variable which sets the number of iterations in the control data section of the PEST control file. I set NOPMAX to 0 and run PEST. It then runs the model once, prints out the objective function and contributions to the objective function by each observation group. These are listed on the screen. They're listed in the run record file. Then I run the PWT-ADJ1 utility to build a new PEST control file in which weights are adjusted such that the contribution to the total objective function by each observation group, which isn't a regularization group, is the same. As usual, to see what the utility does, just type its name at the screen prompt. After running PWT-ADJ1, my situation may now be this. I might say, please make the contribution to the objective function by each group 1000. But it doesn't touch the regularization groups. And here I can see that now the contribution made to the total objective function by each observation group is 1000. So the way it works is that I've got a PEST control file. I run PWT-ADJ1 and that builds a new PEST control file. In that new PEST control file, the weights are changed. Relativity of weighting within observation group stays the same, but the weights between groups are adjusted so that each group makes roughly the same contribution to the initial objective function at the beginning of the observation of the inversion process as every other observation group. Thus, the information contained within each group is visible to the objective function and can flow through to the estimation of parameters. Now I would like to address the question of when does PEST stop, and the ancillary question of should I let PEST run to completion and stop of its own accord, or should I intervene at some stage and stop it myself? The variables which govern when PEST stops, that is the termination criteria, are situated on the 9th line of the PEST control file. Some of them are mandatory, a few of them are optional. I'll always give fairly conservative settings to those variables, as I'll show you in a moment. But normally when I run PEST, I stop it myself. I stop it when the objective function isn't falling very much, or when it becomes clear that it's not going to fall. So by setting those termination criteria conservatively, that tells PEST keep going for a long time, and that gives me the option of stopping it myself, normally after a much shorter time. To stop PEST, simply press Ctrl+C in the window in which PEST, or the Run Manager if you're using PEST or PEST-HP, is operating. Pressing Ctrl+C a few times stops PEST, and the model the model's running in the same window if you're using serial PEST rather than parallel PEST. Alternatively, you could open another command line window in the same folder in which PEST or the behaviour PEST or PEST HP manager is operating and typing the commands pstop or pstop-st. PEST will stop when it sees a little file written by those programs which instruct it to cease execution. Let's have a look at these control variables. We've already discussed NOPMAX in this video to some extent. A NOPMAX stands for maximum number of optimization iterations. That can be set to 0 if you just want to run the model once, have PEST print out objective function contributions and then stop. Set it to -1 if you want to calculate the Jacobian matrix, print out a few statistics and then stop. That will require as many model runs as there are adjustable parameters. A NOPMAX setting of -2 tells PEST to do pretty much the same thing, but don't print out those statistics. Otherwise, if you set NOPMAX to say 50, then PEST will not do any more than 50 optimization iterations. The next three variables tell PEST to cease execution if the objective function isn't changing very much over a few iterations. Very much and how many iterations are defined through those variables. The next two variables tell PEST to cease execution if parameters aren't changing very much over a few successive iterations. How much is very much and how many iterations are defined through those variables. Then come three optional variables which can be useful in certain circumstances. Using the phi stop thresh variable, we can tell PEST to stop execution if the objective function has fallen below a certain threshold. If we're running in regularization mode, it'll be the measurement objective function which has to fall below that threshold. That can be useful when we're doing null space Monte Carlo for nonlinear uncertainty analysis. This last run variable can instruct PEST to do one final model run before it ceases execution, and that final model run should endow parameters with endow the model with optimized parameters. That way, when PEST finishes execution, the model input files have optimized parameters and model output files contain model outputs calculated on the basis of those parameters. Finally, the phi abandon control variable instructs PEST to cease execution if the objective function is too high, on the basis that it probably won't get very low very quickly, and that can be used in, again, null space Monte Carlo circumstances where we're adjusting many parameter fields to calibrate a model, many parameter fields, random parameter fields in succession, and if it's apparent that the adjustment of one particular random parameter field isn't going to give us a low objective function, PEST is informed to abandon it and move on to the next random parameter field. This can be useful when we're doing null space Monte Carlo analysis, the subject of another video. Normally, when I use PEST, these are my criteria for termination. Lots of iterations and very tight termination criteria, which means that I'm not actually going to let PEST do all the model runs that are going to satisfy those criteria. I plan to stop it myself at some stage. But by setting those termination criteria reasonably tightly, that gives me the opportunity to stop it when I want, because PEST will keep continue execution to try to satisfy these criteria, possibly for a very long time, but for no more than 50 iterations. Rarely, if ever, do I allow PEST to progress for 50 iterations. Now let's spend some moments looking at just a few other PEST settings that you may find useful. Let's have a look firstly at this optional variable that's situated at the bottom of the control data section of the PEST control file. Now, at the end of every iteration, PEST writes a file called case.par, where case is the file name base of the PEST control file. This file contains the best parameters achieved to date. This is called a parameter value file, and at any stage of the inversion process, best parameters achieved up to that stage will be recorded in case.par. If you would like a record of the best parameters to date recorded in a series of parameter value files, write the string parsave_iten at this particular point of the control data section of the PEST control file. If you do this, then as well as case.par, which will always contain the best parameters, PEST will leave a series of files which contain the best parameters at the end of each iteration, case.par.1, case.par.2, etc. If you're undertaking SVD-assisted parameter estimation, these files are named case.bpa.1, 2, 3, with case being the file name base of the base parameter PEST control file. To activate that, you answer B to this question that SVDA Prep asks you when you set up SVD-assisted parameter estimation. Why would we want to do this? Sometimes it comes in handy. Sometimes we get to the end of the inversion process and we don't like the parameter field that PEST has come up with. It may give us a good fit with the calibration data set, but maybe we've overfit. Perhaps we like the parameter field from a few iterations back where the fit was still good, but the parameter field was much nicer. If we leave a trail of parameter data files, we have access to these previously best parameter sets and can use them in our calibrated model as the calibrated parameter set. Now let's look at Marquardt lambda settings. As is discussed in other videos, during the second part of each iteration of the inversion process, PEST tries a few different values for the Marquardt lambda, calculating an upgrade vector, a parameter upgrade vector on the basis of each one of these Marquardt lambdas, seeing how well the parameter sets that are calculated that way do in reducing the objective function, and then selecting the parameter set that affects most reduction in the objective function as the parameter set that it takes into the next iteration. The variables which govern how PEST chooses Marquardt lambdas to use are set in the control data section of the PEST control file. This is normally a good set of default variables to use, but the one that I want to draw your attention to is this one here called rlamfac. The method of selection of Marquardt lambdas is done by multiplying a previous Marquardt lambda by a certain factor. That factor can take the Marquardt lambda up or down. PEST determines which is the better way to go on the basis of the objective functions that are being achieved at that stage of the inversion process. Normally it's a good thing if that Marquardt lambda can move fairly quickly to different values if it needs to. By setting rlamFact to -3, PEST will redetermine the factor that it uses during each iteration of the inversion process, so that with only 3 applications of that factor, the Marquardt lambda will be 1. That promulgates a fast-moving Marquardt lambda if the Marquardt lambda happens to be too low or too high at a certain stage of the inversion process. So it's good practice to set that to -3. Note, however, that if you're using PEST HP, you don't have to worry about variables which control the action of the Marquardt lambda. PEST HP takes care of all that itself. But you do need to control the Marquardt lambda or supply values that control the action of Marquardt lambda selection if you're using PEST or BEHAViour. Another variable which is somewhat important is this optional lamForgive variable. When PEST is calculating parameter upgrades after it's calculated a Jacobian matrix, this is where parameters may change by a considerable amount. During the first part of each inversion iteration, parameters are only being varied incrementally. It's in the second part where upgrades are calculated that parameters might vary considerably as PEST searches for a parameter set that lowers the objective function the most. This is also the stage at which a model is likely to fail if it's sensitive to the parameter values that are given to it. Sometimes models are sensitive to parameter values. Their iterative solution procedure may not converge if there's too much heterogeneity embodied in the parameter field which is given to it. And if it fails to converge, it will be, generally, when an entirely different set of parameters is given to it, possibly a set of parameters involving extra heterogeneity calculated in an attempt to reduce the objective function further than it is at the moment. If there's run failure, model run failure, PEST will cease execution with an error message unless lamForgive is set to lamForgive. You just write the string lamForgive at that location in the control data section of the PEST control file. Then PEST will forgive failure of a model run. It will declare that that set of parameters gave rise to an objective function which is extremely high, which is effectively telling itself, don't go near that part of parameter space again. If you're using PEST HP, lamForgive is automatically turned on. A related control variable is dirForgive. This has the same action as lamForgive, but is applied when parameters are being varied incrementally for the purpose of Jacobian matrix calculation. Now, if model run failure occurs under these circumstances, then probably we have a problem. If an incremental variation of one parameter causes the model to fail, then it's highly likely that an incremental variation of another parameter will do the same thing. It's up to you to set dirForgive if you want. The default setting is that it's not on, that PEST will cease execution with an error message if it encounters model run failure when a parameter is varied incrementally for the purposes of derivatives calculation. However, with dirForgive switched on, then PEST will assign the derivative with respect to the offending parameter a value of 0 and then proceed to incrementing the next parameter. Another Marquardt lambda setting is numlam. This is the maximum number of model runs that should be devoted to testing the effects of different Marquardt lambdas. Now, if set to a positive number, say 10, PEST will trial no more than 10 Marquardt lambdas. If during any stage of that Marquardt lambda testing procedure a parameter hits its bound, PEST will take a little time to reformulate calculation of parameter upgrades with the parameter temporarily frozen at its bound. This can now allow the next Marquardt lambda possibly to make greater progress in lowering the objective function, with the inversion process thus reformulated. However, this is an inherently serial procedure and is not efficient in a parallel computing environment. By setting numlam to -10, PEST is instructed to dispense with that serialization procedure that automatically happens if a parameter encounters its bounds, and to parallelize the Marquardt lambda selection and testing procedure no matter what. This may reduce to some extent the efficacy of the parameter upgrade process, but in parallel environments it is far better to keep all processes busy than suddenly trip into a serial procedure which may or may not be more effective in lowering the objective function. PEST HP, you don't have to worry about it. PEST HP takes care of parallelization of the Marquardt lambda process itself. And finally, let me draw your attention to this bound scale control variable. In theory, the mathematics used by PEST to improve parameters leads to a minimum error variant solution of the inverse problem if parameters are all scaled by their innate variability. That is, they are all scaled by their prior variance, their prior standard deviation. Now, we don't do that with PEST because we don't provide the prior probability distribution of all parameters to PEST. That would be a little cumbersome and probably a little subjective. Nevertheless, sometimes if an attempt is made to do this scaling, PEST can perform better. If you set the bound scale variable to bound scale, then PEST will look at the upper and lower bound of each parameter and assume that this is equal to the prior variability of each parameter. Now notice that it takes no account of the fact that the prior probability distribution of parameters should actually be expressed by a covariance matrix and not by individual bounds, so this is a somewhat artificial, though sometimes effective procedure. Anyway, it scales each parameter by the distance between its upper and lower bound and then solves the equations for parameter upgrades. Sometimes this can be quite effective, sometimes not. If you do set the bound scale parameter in this manner, however, you must be careful to ensure that the bounds that you provide to parameters in the parameter data section of the PEST control file do in fact reflect the innate prior variability of every parameter. Sometimes I set the bounds very low and very high, virtually dispensing with the use of bounds, so parameters can go where PEST tells them to, because there may be a message about where PEST wants a parameter to go. It may reflect the true value of the parameter, or it may tell me that a parameter is taking on weird values to compensate for model defects, and in that case I may get some indications of what those defects are. I achieve that through setting the bounds very high and very low for each parameter. If that's the case, then I shouldn't use bound scale. However, if the bounds do reflect the innate prior variability of parameters, then it may be legitimate and useful to use the bound scale control variable. And now let's finish this video with a short discussion of a few useful PEST utility programs. Let's talk about the parap utility first. Parap stands for parameter replacement. At the end of every iteration of the inversion process, PEST rewrites a file called a parameter value file, as we've already discussed. At any stage of the inversion process, the parameter value file contains the best parameters that have been achieved through that process. At the end of a PEST run, the outcomes of that run are recorded in the parameter value file. These are the best parameters, the goal of the inversion process, placed in this file. It's called case.par, where case is the file name base of the PEST control file, or if we're doing SVD assisted inversion, it'll be called case.bpa, where case is the file name base of the base parameter control file. What we will often want to do then is to take these parameter values and put them in a new PEST control file. So suppose here we have our PEST control file on which basis the inversion process was done. The parameter data section will contain initial parameter values. Using the parap utility, we can take optimized parameter values and place them into the parameter data section of a new PEST control file that is in every way identical to the original PEST control file, except for the fact that optimized parameter values replace initial parameter values. Like any other or most other PEST utilities, you can see how it works simply by typing its name at the command prompt, and then next time you run it you can give it the information it needs through the command line. Parap is easy to run. It requires the name of the parameter value file that you want to get parameters out of, the name of the old PEST control file, and the name of the new PEST control file that you want to write, which now embodies optimized parameter values. JCO to JCO is another useful utility. So, as we've talked about already, when PEST calculates parameter upgrade vectors, it does so on the basis of a Jacobian matrix. It takes a lot of time calculating this Jacobian matrix because it requires at least as many model runs to fill this matrix as there are adjustable parameters. PEST calculates this matrix during every iteration of the inversion process and records it in a JCO file. There'll be many occasions, however, where you will run PEST simply for the purpose of calculating that Jacobian matrix. For example, if we're going to do linear analysis or nonlinear uncertainty analysis, or as a preparatory step to SVD assisted inversion. As we've already discussed, we can tell PEST to do that by setting the noptmax variable in the control data section of the PEST control file to -1 or -2, and it will run the model just as many times as it needs to calculate a Jacobian matrix. It will then store that Jacobian matrix in a JCO file. Now, suppose that we take that original PEST control file and we want to change something. Suppose that we want to fix some parameters, tie some parameters, log or unlog transform some parameters, remove some parameters, remove observations, or reweight observations. So now we've got a new pest control file. As long as we've subtracted and not added to the original pest control file, if we want a JCO file which corresponds to that new pest control file, there is no need to then go through the laborious procedure of recalculating that Jacobian matrix through finite parameter differencing. We can simply run the JCO to JCO utility to build the new JCO file corresponding to the new pest control file. JCO to JCO calculates the elements of this new JCO file from the elements of the old JCO file. JCO to JCO is easily run with its information supplied on the command line, the name of the original pest control file for which there must be a corresponding JCO file, and the name of the new pest control file for which we would like the new JCO file. PWT-ADJ1 and PWT-ADJ2. We've already discussed PWT-ADJ1. We'll just discuss it a little further. PWT-ADJ stands for Pest Weight Adjustment. So both of these utilities adjust the weights in a pest control file. They write a new pest control file which bears a resemblance to an existing pest control file. The only thing that is changed in the new pest control file are the weights that are recorded in the observation data section of the new pest control file. So suppose we've got an initial pest control file, and suppose for the moment that this is prior to us having run PEST, so that the parameter data section of that file has initial parameter values. And suppose, as we've already discussed, that we would like to ensure that the contribution made to the initial objective function by each observation group is roughly the same. We can set the NOPMAX variable in the control data section of the pest control file to 0 and then run PEST. PEST will produce a run record file in which it records the contribution to the objective function by each observation group. We then run PWADJ1 to build a new pest control file, and in that new pest control file the observation weights have been changed such that the contribution to the total objective function by observation groups is equalized. PWT-ADJ run is easily run from the command line with its variables supplied through the command line. The file name base of the existing pest control file, the name of the new pest control file, and the objective function that you would like each observation group to have when PEST is run using the weights contained in the new pest control file. PWT-ADJ2 performs a similar function, though with a different emphasis. Normally we would use PWT-ADJ2 not before but after the inversion process has taken place. In this case, we may have used the parep utility to insert optimized parameter values into the parameter data section of the pest control file. We may then set NOPMAX to 0 to calculate a run record file. Or we may set NOPMAX to -1 or -2 to calculate a Jacobian matrix file to give us sensitivities based on optimized parameters as a precursor to doing linear or nonlinear uncertainty analysis based on optimized parameters. This is the subject of another video. Anyway, we set NOPMAX to 0, -1, -2, run PEST, And we get a run record file in which the objective function is computed and contributions made by different observation groups to the total objective function have been computed. Then we can run pwt-adj2 to build a new PEST control file in which the weights have all been changed. In this new PEST control file, the weights become right. When I say right, I mean that ideally the weight should be the inverse of the standard deviation of measurement noise for every observation. Now, if for every observation the weight is the inverse of the standard deviation of measurement noise, and if it's measurement noise that determines the objective function, or more likely, we attribute model to measurement misfit to measurement noise, we calculate an objective function and just assume that whatever causes that misfit is measurement noise, which is not quite right, but we just call it that for convenience. It's actually structural noise or model defects in most cases. But let's assume, for the sake of convenience in doing posterior uncertainty analysis, that model to measurement misfit is explained by measurement noise. So our job at the end of the inversion process is to back calculate a set of weights for which the standard deviation is reflected in the weights. That is, the weight ascribed to every observation is the inverse of the standard deviation of measurement noise. Now, if that's the case, every residual squared will be 1. That is, the residual, the difference between the model output and the measurement, multiplied by the weight, which is the inverse of the standard deviation of measurement noise. On average, each squared residual will be 1, so that the total objective function will be equal to the number of parameters featured, no, not the number of parameters, the number of observations featured in the inversion process. PWT-ADJ2 back calculates weights such that this occurs. That is, such that the objective function is equal to the number of observations in the PEST control file. This can be done for observations as a whole or for observations on a group by group basis, such that the objective function corresponding to each observation group is equal to the number of observations in the group. This then prepares this PEST control file for post-calibration linear or non-linear uncertainty analysis, because not only are the parameters in the parameter data section of the PEST control file optimized, but the weights then have been back calculated to be in accordance with model to measurement misfit, so that calculations that are done by other PEST utilities which look at nonlinear or linear uncertainty of parameters and predictions are operating on the basis that the weights in that PEST control file are correct. PWT-ADJ2 also receives its information from the command line, the name of the existing PEST control file, the new PEST control file, and whether the objective function should equal the number of observations in each group, or just the total number of observations in the PEST control file. We inform it whether to do the weights correction on a group by group basis through this variable. Finally, PREDUNC 7. PREDUNC 7 undertakes linear uncertainty analysis. It calculates the posterior covariance matrix of parameters. Now if we run PEST in estimation mode and we have a well-posed inverse problem, the posterior covariance matrix of parameters is printed at the end of the PEST run record file. This does not happen if we have any form of regularization and/or if our inverse problem is ill-posed. Under these circumstances, calculation of the posterior covariance matrix is a little more complicated. It requires knowledge of the prior parameter covariance matrix. Predunc 7 can undertake this calculation. So suppose once again we have a PEST control file and that this PEST control file contains optimized parameter values. We set nopmax to -1 or -2 and run PEST to calculate a JCO file based on optimized parameters. We then prepare, in ways that are described in the PEST manual, a prior parameter uncertainty file. We can then run predunc 7 to give us the posterior covariance matrix of parameters. This can be very large because if we've got thousands of parameters, that matrix will be very large indeed. It will have the same number of rows and columns as the number of parameters which are featured in the inversion process. Predunc 7 does not receive its information through the command line because there's just a little bit too much information. It receives its information through responses to its prompts. It asks you questions you have to answer. Note that if you've used PWTADJ2 to make the weights right in your PEST control file, the answer to this question is 1, and that makes predunc 7 and other linear and nonlinear analysis utilities that come with PEST easy to use. And that is the end of part 2 of this video.